So, I'm going to be talking about individual fairness in advertising auctions through inverse proportionality. And this is joint work with Shuchi Chawla. So, there's been tons of empirical evidence of skewed delivery in online advertising. So, people from different gender and racial groups can see differing amounts of ads in sensitive categories like housing and employment, even if they're equally qualified to see these ads. So, what causes unfairness? Well, the first source of unfairness is that the advertiser targeting is itself unfair. So, this can be audited by looking at each advertiser's behavior in isolation. The second source of unfairness, which is more subtle, is that the platform's allocation algorithm can create unfairness even when the advertiser bids are fair. So, even when each advertiser bids fairly in isolation. This has been observed empirically in employment and housing ads. So in employment, there's been observed to be skewed delivery in ads, even when there's gender neutral advertising. And in housing, there can also be skewed delivery in ads, even when each advertiser's targeting parameters are inclusive. So the core problem here is that unfairness can arise solely from the allocation algorithm. Our contribution is a fairness framework that eliminates the unfairness introduced by the platform. So we're focusing on eliminating source 2 of unfairness on this slide. Let's give an example to show source 2 of unfairness in a bit more detail. So let's say we have 2 users, Alice and Bob, and 2 advertisers within the tech category. So big tech company and a startup. Let's say that the big tech company and the startup both bid very similarly on Alice and Bob, but the big tech company bids slightly higher on Alice than Bob, and the startup bids slightly higher on Bob than Alice. Let's say that we run a highest bid wins allocation algorithm. Now, Alice is going to see only big tech company ads, and Bob is going to see only the startup ad. The core problem here is that the highest bid wins auction exaggerates small fluctuations in bids. So we actually also showed that this problem is not just theoretical and examined it on the Yahoo Ads dataset. So we showed similarly that the highest bid wins ad auction can be unfair even when each advertiser bids fairly. So we plot here the level of unfairness in the bids versus the level of unfairness in the allocation. So we see even when the bids are almost maximally fair, so they have this level 1 of unfairness, then the allocation can still be unfair. And we're going to formally define what we mean by unfairness in the bids and allocations very soon. So the core message here is that the highest bid wins auction is unfair in theory and also unfair on this data set. Okay, so let's discuss our model. So we consider a simple stylized model for ad auctions in the online setting. We have a universe of users that arrive sequentially, and when a user arrives, each of the K advertisers places bids on that user. So associated to each user is this vector of values, which corresponds to how much each advertiser values that user. The auction allocates a single ad slot per user and potentially randomizing over the K advertisers. So for each user, each advertiser is given a probability, which represents the probability that their ad is shown to that user. And we consider allocation rules that satisfy weak monotonicity so that they can be implemented in an incentive-compatible fashion. As usual, we take the social welfare to be the expected utility of an ad shown to that user according to the considered allocation algorithm. And the unfair optimal social welfare corresponds to the maximum value that any advertiser places on that user. So our goal is to design ad auctions that don't introduce unfairness and to investigate the trade-offs between fairness and social welfare. So there's been a lot of related work on fairness in ad auctions, including our previous work, as well as work with slightly different fairness definitions. There's also been work examining trade-offs between fairness and social welfare, though in different settings. And there's also been related work on different notions of fairness in many other applications. Okay, so how do we define fairness in this work? Well, we consider a fairness constraint expressed as a stability condition. So our starting point is individual fairness. Similar users must obtain similar allocations. So since we're focusing on eliminating the unfairness introduced by the platform's allocation algorithm, we formalize fairness as a stability requirement. If two users have similar values from all advertisers, then they must receive similar allocation. So this stability requirement hones in on the unfairness introduced by the allocation rule rather than by the advertisers. So more formally, we define value stability as follows. We have a value stability constraint F that takes as input a multiplicative ratio between values and outputs the maximum allowable difference between allocations. So let's say we have a pair of users, and each advertiser bids within or has a value within a factor of lambda on the two users. Then we require that each advertiser's probability of being allocated their ad to each of the users is within f of lambda. So this is an L infinity constraint on the two allocation vectors for these two users. So here we measure closeness and values multiplicatively so that our definition is scale invariant, and we measure distance and probabilities additively so that the difference corresponds to the probability that the two users have different outcomes for that ad. So this value stability definition captures that the auction does not introduce any further unfairness other than what might already be present in the advertiser bids or values. Okay, so let's now examine different value stability constraints. So that's that function f in the definition. So here we plot a family of value stability constraints of the form 1 minus lambda to the negative 2L. So when L is very small, this value stability constraint is very strong. And as L gets larger, the value stability constraint weakens. So this sort of captures a range of strengths of value stability conditions. Okay, so with that definition in place, let me describe our algorithmic results. So we examined the trade-off between value stability and social welfare. So we designed value-stable ad auctions that achieve a constant fraction of social welfare compared to the unfair optimal. Our auctions also achieve the near optimal trade-offs between value stability and social welfare under mild assumptions. In addition, we extend our results to stronger notions of fairness. So first, we extend our results to fairness over subsets of advertisers, which gives guarantees over subcategories. Then we also extend fairness to the multi-category setting considered in our previous work. We also provide experiments on the Yahoo dataset, and these experiments are present in our paper. So for this talk, we're going to focus on the first set of results described here. Okay, so our goal is to design value-stable allocation algorithms. So recall our value stability condition here for a value stability constraint F. And let's now look at the approximation ratio for social welfare. So this is the social welfare achieved by our allocation algorithm divided by the maximum possible social welfare, which we refer to as the unfair optimal. So our goal is to design value-stable allocation algorithms that achieve a near optimal approximation ratio. Okay, so what's a first attempt for such an allocation algorithm? In our previous work, we proposed proportional allocation. So the idea here is to allocate proportionally to the values. So we set an allocation proportional to the values as follows. So the probability that we assign to an advertiser on a user is how much that advertiser values the user divided by the sum of how all the other advertisers value the user. So this satisfies value stability. And intuitively, the reason behind this is that it's smooth. So unlike the highest bid wins allocation rule, it doesn't magnify small differences in the values. And so it holds, value stability holds for F of lambda equals 1 minus 1 over lambda. So that was within that family of value stability constraints that I described previously. The problem with proportional allocation is that the approximation ratio goes to 0 as the number of advertisers goes to infinity. And let me give some intuition for why this is the case. Consider a value vector that consists of one advertiser bidding highly on the user, and then a bunch of advertisers bidding very small values on the user. So that's gamma written here. Now, proportional allocation is going to assign a probability on the value of 1 that depends on the number of advertisers. And in particular, as the number of advertisers goes to infinity, the sum of all of these tiny values is going to also get very large. So the probability placed on the advertiser who values this user 1 is going to go to 0. So as a result, the social welfare of this allocation rule goes to 0 as the number of advertisers goes to infinity. This problem is not just for the proportional allocation algorithm described here, persists for any allocations that are proportional to any function of the values. So in order to achieve better trade-offs between value stability and social welfare, we need to move outside of the class of proportional allocation algorithms. So our solution is inverse proportional allocation. And our core idea is to deduct proportionally to the inverse of the values. So we start by allocating a single ad slot to all of the advertisers, and then we slowly start deducting proportionally to the inverse of the values. So that's according to the blue arrows here. And we keep deducting until the purple rectangles, which represent the remaining allocations, sum to 1. So there's actually a max with 0 because we need to ensure that all of the allocations are non-zero. So once an allocation reaches 0, we remove that advertiser and we continue deducting for the other advertisers. So we show in our paper that this value t can be computed efficiently. So we provide an efficient implementation of inverse proportional allocation in the paper. So now let's talk about the performance of inverse proportional allocation. So the first property is that it achieves an approximation ratio of 3/4. So this is a constant regardless of the number of advertisers in the system. So this represents a very sharp distinction against proportional allocation, which had its social welfare go to 0 as the number of advertisers went to infinity. And here, the crux is that this inverse proportional allocation much better handles when there's one high value and a lot of tiny values. Second property of inverse proportional allocation is it's able to maintain this approximation ratio while also satisfying value stability. So we get value stability with respect to f of lambda equals 1 minus 1 over lambda squared. So it's also in that class of value stability constraints that I mentioned before. And so the key insight here is that inverse proportional allocation can achieve value stability and a high social welfare, even as the number of advertisers goes to infinity. So far we considered deducting proportionally to the inverse of the values, but we can generalize inverse proportional allocation to deduct proportionally to a function of the values. And the reason we do this is to capture a more rich range of value stability constraints. So we set t so that the sum of max of 0 and 1 minus t times this function applied to the value that the advertiser I places on the user is 1. So it sort of takes the same structure as before. Now we show that inverse proportional allocation with g of x equals 1 over x to l is value stable with f of lambda equals 1 minus lambda to the negative 2l. So the key idea here is by tuning this function g, we can achieve different value stability constraints. So this sort of gets us all of the value stability constraints in the previous diagram that I showed before. We also show that inverse proportional allocation with this function g achieves an approximation ratio that depends on all L, but is independent of the number of advertisers. And this approximation ratio goes to 1 as L gets larger. So let's look at the limiting behavior of this family of inverse proportional allocation algorithms to get a sense of what they're doing. So as L goes to 0, inverse proportional allocation with g of x equals 1 over x to L just turns into equal allocation. So it allocates equally to all advertisers. This, of course, does not achieve non-trivial social welfare guarantees. As L goes to infinity, g of x equals 1 over x to L approaches the highest bidder wins allocation rule. So it's getting the optimal approximation ratio, but is not value stable. And what we showed before is that L equals 1 sort of is able to achieve a constant fraction of the social welfare compared to the unfair optimal while also being value stable. And we can sort of tune that this trade-off by tuning L. So our first result is that for the family of value stability constraints, f of lambda equals 1 minus lambda to the negative 2L, these inverse proportional allocation algorithms achieve the optimal approximation ratio for social welfare as the number of advertisers goes to infinity. So this is sort of the best that one can do for this family of value stability constraints. We also look outside this family of value stability constraints and show for any value stability constraint satisfying a very mild condition, there exists an inverse proportional allocation algorithm that's value stable and achieves the worst case approximation factor shown here. So the idea here is that it achieves roughly a constant fraction factor approximation to the optimal approximation factor for the constraint f. It's not quite a constant because there's this log term here. So in summary, we get an inverse proportional allocation is near optimal for general value stability constraints. Okay, so now let's discuss some of our experiments. So first, we empirically validate on the Yahoo Ads dataset that inverse proportional allocation is value stable across the full spectrum of values of this parameter L. So here we plot essentially the bid unfairness. So we only consider allocation or bid vectors that overlap on sufficiently many advertisers. So in practice, not all advertisers bid on all users. So we have to sort of only consider allocation vectors that are sufficiently overlapping. But when we make these modifications, we describe in detail in the paper and appropriately measure the ratio between bids, we get the following curves. So here we plot the ratio between bids and we plot the 90th percentile of the allocation difference. And we see that we achieve value stability and the level of value stability strengthens as L is reduced. So this is aligning with our theoretical findings. Secondly, we compare inverse proportional allocation to proportional allocation. So here we plot the parameter L used for these, like, of the value stability constraint against the approximation ratio. So here we plot this for slices of the data set consisting of of users who receive 2 bids, 3 bids, and 5 bids. So for 2 bids, proportional allocation slightly beats inverse proportional allocation, but for 3 or more bids, inverse proportional allocation consistently outperforms proportional allocation. In particular, this distance gets larger as k increases. So there's already a substantial difference when for 5 advertisers. And this aligns with our findings that inverse proportional allocation much better handles the presence of more advertisers with respect to social welfare. So in conclusion, we considered fairness in ad auctions and formalized this as value stability. We designed a family of allocation algorithms that achieved a constant fraction of the social welfare compared to the unfair optimal and near optimal trade-offs between fairness and social welfare. We also extended our results to subset fairness, which is fairness over subsets of advertisers, and the multi-category setting, which allows for many categories of advertisers. Thank you.